Chapter 11, Vector Valued Functions, Section 11.1, Vector Functions and Their Derivatives. And what I want to start out with is a little introduction to the whole idea of vector functions. What we're very used to is seeing a little plot, and I'll just make a little quick plot here, where here we have x and y, but we can think of y here as really f of x. And when we plug in different values of x, we get different results. And if it was y is equal to x squared, we'd get, a parabola like this. Or if we had something a little more complex, x, and now we're going to have this f of x going to be cosine, we get a cosine function. So we're used to seeing those sorts of things. And those regular functions are called scalar functions. But we could write a vector as a composite of, or made up of components of scalar functions. So if we have, imagine a vector little r, we'll say it's equal to the x component will be something like f of t, oh come on Cliff, f of t, and because that's the exponent, we're going to multiply it by I, plus then another function, g of t, this is just another scalar function, times j, plus h of t times k. Okay, so that's basically the x component of our vector r is equal to f of t, y component is g of t, z component is h of t, and depending what these vectors are, we could get something in your book. For instance, they make it look like this, where we've got a function kind of arcing off like that. Now, what is the vector looking like? Well, at time t0, it connects the origin to that point. At time t1, some other time, it might be connecting the origin to that point, right? So basically what would be happening here is if f of t is this function right here, at time t, we would plug in our t function like this, and we'd get a value for the x. We'd plug in t here, we'd get our y value, and that would be here, and then we'd plug in our z value, we'd plot those out like this, and then we'd have our vector r. And through time, of course, because these components are changing, the position or where that vector is pointing changes. And basically that is what a vector function is. Now, let's just try one here just for fun. Scoot down a little bit. And let's plug in and say, and like so this just gives you a feel for it, it's in your book, r sub t, ooh, I'm still red. Let's get back out of that. A little too violent. Is equal to cosine of t I plus sine of t j plus, and then we'll just make this t of k. Now what is this going to look like? Well, if we just start out by looking at this scalar function right here, just this one little part, well, we say, well, we know what that looks like. That's a cosine curve as a function of t, and it looks like that. What's this sine looks like? Well, we kind of know what that looks like too. That's a sine function, and it looks something like this as a function of t. And tk, well, that's just going to be a straight line relationship like that. Okay, so as this is just x is equal to y, so we just get a relationship like that. These are the component parts. If we put two of them together and we just think about cosine t plus sine t, we actually know what that looks like. That's just our unit circle, right? And we know that, but we can think of this as a vector. There's our r vector at different positions, and here it's pointing off at 0, here it's pointing off in this direction at pi, etc. Now if we add t, this final thing for z, I'm going to have to now draw it kind of in 3 dimensions. Now we've got, here's where our circle would be in the xy plane. But then we've got z like this, and so what this becomes is our circle lifts off and it doesn't get bigger, but you can see better. It becomes a spiral or a helix, okay? And by manipulating these values, we can get different forms. For instance, if we want something a little more exotic, we could substitute in cosine t here, and then instead of z going up uniformly, it would now kind of go up and down. And you can kind of imagine what that would look like.